Okay, we'll go ahead and get started. Respond to the poll if you haven't done so already. I have a couple things I want to talk about. Okay, so one was I wanted to look at this algorithm called the Nelder-Mead. But then before that, I thought, maybe we could talk a little bit about DataFest. And I guess I'm assuming that most of you have signed up for to participate in DataFest, and maybe you haven't heard back if your team was accepted or not. But I hope that's the case. I don't know who has at least signed up or like submitted a team entry. Okay, a handful of you, and who participated last year? Okay, and did any of you guys place or at least move to the finalist round? Some of you, yes? Okay. Well, I want to just kind of talk about, what, in my opinion, this is my opinion, not fact, but in my opinion, for what makes a good kind of DataFest effort and submission and things like that. And so, DataFest is coming up in like 2 weeks, okay, or 3 weeks, I don't know. It's end of first week of spring quarter. So when's that? So we have it's soon, okay? And so what you will see is you're probably going to get we're going to get some kind of giant data set. Usually it's multiple gigabytes or at least a couple hundred megabytes. It's usually a very big thing, usually much bigger than anything that you've dealt with before, okay? So number one piece of info is do not use read.csv. That's going to take way too long, okay? You can try using read_CSV. That also might take long. Probably the fastest thing to get your data in is going to be function fread from data.table, the package data table. And so, it might be worth taking an hour over the weekend or something to familiarize yourself with some of this stuff. Okay, here's my first tip, okay, is that one compelling question and investigation is much stronger than several weaker topics and analyses, okay? So sometimes during the presentations, we'll see, so during DataFest, I will not be a judge, okay? But I will be there during the weekend, and I'll be there to offer, my advice and counsel if you want it. I'll just be kind of walking around, and if you see me, say hello and say, introduce yourself and say, we have some questions or whatever. I'm happy to try to give you some of my thoughts regarding, ideas to consider. But anyway, during the presentations, we'll see different stuff, and sometimes some groups will try out like multiple things and investigate several different things all at once, and that's fine. But usually, I would say sticking to one compelling question and investigation and delving deep into that is going to be stronger than a bunch of different things, okay? And so what this will often mean is that, in the beginning, when you're just kind of familiarizing yourself with the data, just explore multiple ideas. Say, is this possibly related to this? What pattern might we see? What kind of stuff will we see? But once you settle on a topic as a group, you should say, this is kind of the topic that we want to go dive into. Stay with it and delve as deep as you can and explore maybe different facets or aspects of that topic. And check those things out, okay? And so my recommendation as far as your time goes, Friday night should be spent familiarizing I'll write familiarize yourself with the data and explore multiple ideas. Okay, so become familiar with what kind of stuff you will see in the data, and from there explore ideas. And then by Saturday morning, you should have an idea locked in. Okay, so sometime Saturday morning, you guys get back together Saturday morning, having the idea locked in, and then spend Saturday devoted to kind of fully exploring the idea or question. Okay, and you can tweak the idea and question that you're investigating. Okay, but you shouldn't just abandon the topic and try something brand new, Saturday night or something like that. Okay, tweaking the question is fine, but don't just abandon it. So that's kind of my my recommendation. Saturday should be spent exploring this, and then kind of putting Sunday will be putting your presentation together. Okay. Okay, so then the question now is, what makes a compelling question and investigation? So if we're going to say you should come up with one topic that's a compelling thing, what makes a compelling question and investigation? I think this is, so there are a few things. So probably the first thing that makes a compelling question is being able to answer what variables are related to each other. Okay, what variables are related to each other beyond what would be completely obvious, right? Beyond the completely obvious relationships, and probably the most useful tool will be using dplyr, package dplyr. Filter, mutate, group by, summarize. This will probably be the most useful part as far as exploring, what kind of variables are related to each other. What proportion of category A has this feature versus what proportion of category B has this feature, or something like that, right? Questions like, what proportion of category A has, feature X versus what proportion of category B has feature X, right? And if there's a significant difference, then maybe that's worth exploring, okay? Or just what's the average for has feature X, or what's the mean for category A versus the mean for category B, things like that. Okay, those are that's where dplyr is going to come in very handy. And so refamiliarize yourself with your dplyr notes. Okay, other questions? Maybe under which conditions or settings does some other variable produce high or low values? Okay, and so we don't what the data set is a secret until the actual day of the competition, and so it could be whatever it could be. These questions may or may not even be relevant. Okay, these ideas here, but it might be interesting to explore what conditions or settings produces high or low, particularly high or low values, or something like that. Okay, so again, this is kind of related to what variables are related, but here it's specifically we expect there to be some kind of relationship between these two things, and if we further explore that relationship, we can see that under these conditions is when you get kind of your largest or smallest values. Okay. Or another question is, are there common traits among outlier values? Okay, a lot of times we see outliers as inconvenient things that we don't know how to explain. But perhaps if you devote your analysis to the outliers, you might find something interesting among the outliers. You know, the listings that have the, you know, highest number of views or something. You know, what videos on YouTube have, like, you know, 1 billion views. These might be the outliers, but that might be the most interesting part of the analysis, whereas all the millions of videos that have under 100 views, that might not be as compelling. And so maybe there's something there among the outliers. Okay, so that in of itself could be an exploration. Okay, and I would say, you know, explore a bunch of these things, and then try to agree upon some kind of analysis. Pick the variables that you want to explore. Okay. Another thing to keep in mind is that with such a large data set, it's often impossible to consider all cases in everyone. Okay, so, you know, you might have, I think, you know, last year, well, I guess last year the data came from job posting information from Indeed.com and things like that, and it was a massive data set. Okay, and to try to come up with some kind of conclusion or relationship for everything that appeared in that data set, it was a very difficult. It was a difficult task to try to even pursue. Okay, so instead of trying to consider some kind of trend that exists in the entire data set, it's often useful to segment the data and explore just maybe a few categories of interest. Okay, so maybe you're just interested in just a portion of the data, and you find some kind of trend or relationship or something worth exploring there, and that only that might allow you to find an interesting trend or relationship, but and it will also speed up your computations, because you're only dealing with a kind of a subset to do the summary things. Okay, and so one thing, you know, I saw a lot of groups doing, and I think it helped them, was that rather than trying to look at all the jobs that appeared, all the job listings that appeared in the data set, okay, because it was like, you know, I guess people go on Indeed and they companies will post a job listing, and then applicants will view the job listing, and I guess they were looking at, you know, view counts and things like that, rather than looking at the entire data set, which was kind of too crazy. Maybe they said, you know, let's only look at jobs in a certain category, or only jobs in a certain region, or something like that. And then within the listings that appeared in that category, then they did an investigation on, you know, what variables are related to view counts or things like that. Okay, and that's still a compelling analysis. Okay, it's okay that you're not looking at the entire thing. You can just say, we as a group decided to focus on this segment, and for this segment, this is the interesting things that we have found. Okay. Is that okay? Are there questions about that? Okay. I want to talk a little bit about the presentation. So all of your work is going to kind of boil down, and your group will make a presentation. Okay, the presentation, just because there's so many groups, your presentation will be limited to 5 minutes, and you get 2 slides. Okay, and that's how the rules were last year. Or was it different last year? Any of those who you competed? I think it was 5 minutes and 2 slides, right? Anybody confirm that? No one. Okay. All right. I'm pretty sure that's what it was last year, and I have a feeling it's gonna remain the same. Okay. 5 minutes, 2 slides. Okay. And here's the thing: this is not a class project. Okay. It's a you don't need to prove to your professors or whatever that everybody in the group contributed, okay? It's the culmination of what your team has done, okay? And so this is kind of my recommendation, at least for the 2 slides, and you don't have to follow this, okay? Slide 1 will kind of fully describe the question you're investigating, or at least, and maybe some introductory summary stats kind of supporting the question that you've investigated, right? So if you're doing like, does the seed yawn make a difference in whether a person yawns or not? That's going to be kind of the question, and you'll say like, these are the variables we looked at, and here's a 2-way table that says, 4 out of 16, this and that happened, 25% versus 29% or something, okay? And then slide 2 will kind of probably be your charts and graphs, results of your exploration and or analysis, okay? There is a category for winning for best visualization, and if you're gonna go for best visualization, maybe you want both slides to be visuals, but probably if you just do like one really impressive visualization for slide 2, that's probably enough to win it as well, okay? If the best visualization. So make your chart graph visualization. This is kind of my recommendation, all right? And then my other recommendation, it's okay if not everybody talks, okay? And I feel like sometimes when you have a group project of like 5 people, all 5 people want to say something. And if that's what your group decides, that all 5 of you are going to speak, then that's fine. But in 5 minutes, every time there's a transition between speakers, there's a little bit of this transition lag time, okay? And it can be a little bit distracting within a short 5-minute period, okay? And so if just one person talks the whole 5 minutes, that's fine. If 2 people talk during that 5 minutes, I think that's also okay. Probably within your group, somebody is more eager to talk than the other people, and it's okay to give play to your team members' strengths. Okay, there's no need to force somebody to talk if they don't want to talk. So look at your team member strengths, and if somebody enjoys speaking in front of everybody, let them be the person. Okay. And that's kind of what I have to say. Is that all right? And then finally, think about where your data is coming from, because it's probably not going to be a random sample, right? And so a lot of these traditional statistical tests, like a t-test or whatever, comes with the assumption that your data is a random sample. And most likely, at least in the years past, the data were not random samples. And if they're not random samples, you can't treat them as random samples. Okay? Think about where your data comes from. Think about what process produces the data, okay? And what will your data be lacking, okay? These are good questions to consider, and your data is unlikely to be a random sample, and if it's not a random sample, you cannot treat it like a random sample. So even if you have like 2 million rows, you can't treat that like a random sample that will then generalize to the population or something like that, okay? You can compare things within the data set and you can say stuff about that, but you cannot generalize to the entire population. And so that's just something to be mindful of, okay? I've seen teams in the past make conclusions that were not sound because they were treating the data as if it were a random sample. I'll tell you the same anecdote that I told my other class, that the other class was that, so in World War II, the British Air Force, had these, bombing campaigns over Germany and, occupied Europe. And, a lot of the bombers were shot down and never returned. And so the Air Force, said, let's figure out ways to strengthen our airplanes so that more of our pilots come home. Okay, that was the idea. And so they got a statistician, they got some engineers, they did a whole data collection survey of basically all the airplanes and where they saw damage and things like that. Okay, and so they went through kind of all of the airplanes that they saw, and they said, okay, we're noticing lots of damage in kind of the wings and the tails and things like that. Okay, and they said, okay, so here's our data. Their data report says these are the areas where we see damage to the aircraft, and so the question is, for our engineering team and their statistician, where should we work on improving our airplane strength? Okay, where should we kind of add armor and improve the strength of the aircraft? All right, and what do you guys think? Yeah.
What they're gonna say, put on the wings.
Okay, so the natural response is to say, let's strengthen the places where we've seen damage. Okay, that's kind of the natural response. Okay, but the statistician said, I don't know what he said. Okay, but basically, the thought process of the statistician was, let's think about what's producing our data. Why are we seeing the data that we see? Okay, and the statistician said, these are the airplanes that made it back after the bombing campaign. These are the airplanes that got damaged and they still made it back to our airfields so that we can survey the damage. There were a lot of airplanes that got damaged and did not make it back. Okay, and so if we think about the process that generated our data, and we think, why did some airplanes come back and some airplanes not make it back? The reason why, the natural conclusion is that for the airplanes that came back, the damage they incurred was not critical, and the airplane was still able to fly. The airplanes that did not make it back, the damage they suffered was critical and caused the airplane to crash. Therefore, rather than strengthening the places where we see damage, we should strengthen the places where we did not see any damage. And because the damage to those locations might result in airplanes that crash, okay, or did not make it back. And so kind of counterintuitively, this is what they did. They said, this is where we see damage on the airplanes. We are not going to strengthen these areas. We're going to strengthen everywhere else, okay? And indeed, making those changes improved the airplanes that made it back and things like that, okay? And so this is, it seems kind of counterintuitive, but by keeping in mind the process that generates the data that you see and not treating it just as a random sample or something that's representative of all the data, can result in the important changes that need to be done. Okay. Well, anyway, I don't know if you guys have any other questions. No one's really worrying about Data Fest right now because it's 10th week and finals is around the corner and stuff like that. But I hope you guys, I hope to see you guys there. And if you see me wandering about, don't hesitate to say hello or ask me for, I don't know, tips or advice or things like that. I'm happy to kind of help and whatever. And make sure you get sleep that weekend. Okay, sleep is Very important. Make sure you get your sleep this weekend as you study for finals as well, okay? Your health, your mental health is very important, and sleep plays a significant factor there. Okay, I want to talk about the Nelder-Mead algorithm, which I think is it's a really cool thing. I mean, these are the things that I get excited about. Okay, so the Nelder-Mead algorithm is an algorithm that we can use in higher dimensional data, okay? Or for optimization. So if you want to optimize some kind of higher dimensional function, you can use the Nelder-Mead algorithm. We covered one multivariate optimization method, and what was that? Coordinate descent, right? And coordinate descent basically said, I don't know how to do multivariate stuff. We're going to reduce our multivariate problem into a univariate problem, and we'll do univariate optimization, one variable at a time, okay? And so that's what coordinate descent is. The Nelder-Mead algorithm, in 2 dimensions, or even it works in higher dimensions, works by using what it calls a simplex, okay? And so if you have some kind of function that has a function of 2 variables, it exists, basically its domain is a plane, okay? All of x1 and all of x2 or x and y or whatever it is. You have a function of 2 variables, and to kind of select a kind of what thing will define the plane will be a triangle, okay? You need 3 points to kind of define a plane. And if you want to define a space, you would need 4 points, right? You would have the triangle with another point, and you get this tetrahedron pyramid shape, and that will define your space, assuming they're not all collinear. And if you have 4-dimensional space, then you need something with 5 points, okay? And so the simplex basically has 1 more point than the number of dimensions, and that's what we have. We've got n dimensions, and you'll have a simplex with n plus 1 points, okay? And what we are going to do is we are going to take a look at our simplex and evaluate the function at all of the vertices of the simplex. So in our 2-dimensional thing, we've got a triangle, and 3 points in the triangle. We're going to evaluate the function at all 3 points, and we're going to rank them from best to worst, okay? And so we're going to start off. So imagine a contour plot where you throw down a triangle, and you're going to say here, what is the, because contour thing, we want to get to the bottom of the hill, right? We want, or bottom of the valley. We want the optimal thing. We're going to rank these from best to worst. So we're going to take, what is the value of the function at this location? What's the value of the function at this location? What's the value of the function at each of these corners or vertices? And we're going to order them from best to worst, where the smallest value is best and the worst value, the largest value is worst, okay? And from there, we are going to propose a few different locations. What we want to do is we want to replace the worst point, okay? Get rid of the worst point in this triangle and replace it with another one, okay? And we don't want to just get something that's a little bit better, okay? Because if I just nudge this a tiny bit and this gets a little bit better, but it's still worse than V, then I haven't really made much of an improvement, okay? U is still better than V, and V is still better than W, even if W is not as bad as it used to be, okay? What we want to do is we want to find a value of W that is better than V. Actually, we might even want it to be better than U, okay? And so we just want a proposed thing where we're going to kind of replace the worst point with a new point that is not only better than the current worst point, but it's better than the second worst or better than the best point, okay? And so these are kind of the proposals, okay? And first we start with a reflection, okay? So the worst point, we reflect the worst point through the centroid of the remaining points to get our reflected point R, okay? And we evaluate the function at R, okay? If it's between, if this thing is between the best point and the worst point, then we'll go ahead and replace the worst point with R and move on to the next iteration. Okay, so we're going to just kind of reflect W with R, and if it's better than that, we'll go ahead and replace W with that. Okay. On the other hand, though, if this point ends up being even better than U, okay. So if we reflect it, and it turns out that this reflected thing is not just better than V, but it's better than V and U, then we will say maybe I can be a tiny bit greedy and take an even bigger step, okay? And so we're going to reflect it and extend it and see if this one's even better, okay? So we're gonna, we start off with this triangle. We reflected it. If R is even better than U, then we just try out, maybe I can crank it up just a little bit further, and I would propose the extended point, okay? All right, and if I extend this, then we get, and if this is even better, then we will accept the extended point, okay? If we've gone a little bit greedy, but we overstepped it, so that it's not actually any better, then we'll fall back and just accept the value R. Okay, so we reflect this. If this is better than V or U, then we'll take better than V but not better than U. We'll just take this point. If it's better than U, then we'll try extending it to just see if we can be a little bit greedy. And if that's better, then we'll take it. And if it's not, we'll just use the R. Okay. On the other hand, if we propose R and it's not better, it's like better than W, but it's not better than V, okay? Meaning the best point is U and the second best point is V, and R is still the worst point, then we've got to try something else, okay? And so then we try these contractions, okay? So we've got, first we reflect, if we might extend, okay? But if this is not the case, okay, where the reflected point is not better than V, okay, then we will try a contraction, okay? We'll say, well, maybe we'll try this contracted point where it's just halfway between W and this midpoint, or we'll just try it where it's reflected past this, but not all the way out to R. Okay, so we try this, and whichever one of these is best, so we propose both of these at the same time, whichever one of these is best, we will take. Okay? And if none of these are better, okay, if none of these are better, like if CI is not better than this, or the CO is not better than V, then that means none of these points that we've proposed, R, CI, or CO, are better. And so what we are going to do is just shrink the triangle down to here, okay? And we'll just work with a smaller triangle. And so maybe all of this will make a little bit more sense if I kind of graph all of this stuff here, okay? So let's start with our environment, and we'll try clearing this. maybe I will do we'll try this. All right. So here I have the this thing. Here's my two-dimensional function, and what I'm going to do is okay. So we're going to just start off here, and my initial triangle, my initial simplex is going to be the points 0, 0, 0, 1. I'm sorry, 0, 1, and 1, 0. Okay, 0, 1, 1, 0. So that's what I have, and I'm going to go ahead and I'm going to just go ahead and plot this thing here. Okay, and so what my function is going to do is it's going to take in these 3 input points, and it's going to return the next 3 points that it should use. And I'm going to go ahead and I'm going to try this. I modified the code just now, so maybe it won't be as good as I had hoped, but we'll see. So I'm going to go ahead and just run this. That is not what I wanted to see. Sorry. Okay, let me just delete this plot. I'll try this again. Am I seeing something wrong here? Not sure why I'm getting. Okay, I will just remove these modifications that I've thrown in here. So what we will do is we're going to create this thing. So here's our initial plot, and what I'm going to do is we are going to propose basically a few values. Okay, so right now, if we look at this, if we look at the contour plot, we can see that this is going to be our best value. That's u, and these are quite close, but this is our next best v, and this one is our worst. Okay, and so here I'm going to find kind of the midpoint or the centroid of u and v, and I'm going to reflect w across this. So I'm going to take this vector from here and I'm going to just basically add it. And so I'm going to propose this. Okay, and when I propose this, this point is actually even better than u itself. And so when I see that, I just say, well, maybe I can be a tiny bit greedy. And so this is going to be my r. And I'm going to say, maybe I can be a tiny bit greedy and go a little bit further and propose this. Okay? And this is going to be the best one there. And so with that, I'm going to accept this point. And I'm going to come back and I'm going to say, you know what, let's use, for our next triangle, we're going to have these points here, U, V, and E, okay? And so when I do that, which one is the, so this is now my next thing. This is gonna be the best point that I have, okay? This is my second best point, and now this is my worst point, okay? So I'm gonna find the kind of the midpoint here, and I'm going to propose a reflection across here. So this is gonna be my reflected value R, and because this one is probably better than U itself, I'm gonna say, well, let's just try being a little bit greedy. And I will propose this, okay? And when I do this, I'm gonna find that, okay, E is not actually any better, so we will not take E, okay? E is not better than R. We can see that it moves it further up the contour, so we're not gonna take that. And so here, I'm going to just, for my next iteration, I will accept this as my triangle. Okay, so for my next iteration, maybe I will just draw this. My next iteration is this, okay? And we're gonna say this is the worst, best, U, V, and now this is the worst, okay? And then, and so I reflect this across the midpoint, and I propose this point. This is gonna be my reflection. And then this is probably better than U and V, just kind of visually looking at it, so I'll also propose the extended one. This one does not look to be better than R, so the next value I'm going to use is going to be this. Okay, so I'm just drawing kind of these triangles, and so so my next iteration will use these things. And so now I don't have contour lines to kind of help me, but it looks like this is the best, and this is the next best, and this is the worst. I'm not entirely sure, okay? And so I try reflecting. This is worse than U or V, so I'm not gonna take that, okay? And then so in this case, I'm going to propose contractions. I'm gonna say, of these, which ones are better, okay? And probably this one, okay? I'm not entirely sure. And so for the next iteration, it might be something like this. And now I relabel my points, and this is gonna probably be U, V, and W, and then we just continue the algorithm accordingly, okay? So this is kind of what we wanna see, and let me see if we can see that here. Oops, maybe. So what I have is I've got system sleep. Yeah, maybe I'll just increase this to 3 seconds here. Okay, so I'm gonna just kind of draw our thing. We'll run this, and so here is the, oh, I gotta stop this because it's flooding the points. Okay, so it starts there, and it's going to say, all right, here's the reflected, here's the best one, okay, and it tried this. The reflection, the extension was no good, so it takes that. Here, the reflection is the best one, not the extension. Oh, and this was the worst, so it reflects it this way. And right now, all the reflections are best, and the extension is no good. At this point, it tried the reflection, but then it was the contraction, and then it goes this way, and it keeps trying, and it just moves smaller and smaller. It keeps going, all right? And so this is the Nelder-Mead algorithm. It moves, and it adds these kind of, proposes these things, and it moves down, and so at this point, kind of the best value that it settled on is we'll just kind of take the mean of column means of x, okay? And so right now our best location is 2.373 and 2.537, The optimum value, if you do the calculations, is at 2.25 and 2.5. And so we can see that our algorithm has kind of moved in and closed in on that location in this mechanical way. Without the calculation of derivatives, it just has to calculate kind of a bunch of vertices at each location to decide where to go next. Okay, I think it's a pretty neat algorithm. I'll post this handout that talks about it, and we'll end there. We'll see you guys on Friday.